let's do that next. Here we can say, converting from parametric equations to function, say x and y. Okay, and this method here, method is called eliminating the parameter. And we'll see pretty quickly why it's called eliminating the parameter. Let's get my pen here. And I think I want to start with kind of a general steps here, maybe I'll say. Like in general, these are the steps you'll want to take for this eliminating the parameter method, okay? And so remember, the goal is we start, what do we have? We start with parametric equations. Now let's say x equals x of t, y equals y of t. And we have some bounds, say t1 and t2. Okay, and what's our end goal, right? Well, the end should be something that looks like y equals f of x, where there's no t, no parameter anymore. We've eliminated some parameter from this system here. And here's the steps we can take. The first step is to solve one of these equations. So I'll say solve either of these for t explicitly. So it will look like then like t is then a function of x, or t, so maybe I'll put or t equals a function of y. So you pick one of these parametric equations and you solve for t instead of, so like in these, we have them solved for x in terms of t, but you want to solve either of these equations for t in terms of whichever variable you picked, right? So if you pick the equation x, you want to solve for t in terms of x. If you pick y, same thing for y. Once you have that, the next step is to plug t into the other equation, into whichever one you didn't pick. So I'll just put other equation. Okay, and then the third step is to solve for y. In terms of x. And that will get you something that looks like y equals a function of x. And so here's kind of a good step-by-step. And what I want to do over here is an example and number our steps. So we kind of mimic what these steps look like here. So where are we starting? We're starting with some parametric equations. And for this example, let's look at, say, x equals the square root of 2t plus 4 and y equals 2t plus 1. And let's say this is over the time interval -2 to 6. Okay, and so here's where we're starting. We're starting with parametric equations. And what's step one? Step one is to solve either of these for t. Well, when I look at these, I'm free to choose whichever one I want. I notice here that the equation for y looks a little easier to solve for t. Not much easier, you know, they're both pretty simple, but here we can just say, well, then if y equals 2t plus 1, then we have 2t equals y minus 1, which gives us t equals y minus 1 all over 2. And that concludes the first step, right? We picked either x of t or y of t, and we solved it for t explicitly in terms of the other variable. And so now we have t equals y minus 1 over 2. So what's step 2? We plug this into the other equation. Well, if we plug this into the other equation, we didn't use x, so then we're going to have to say x equals the square root of 2 times t, but now t is y minus 1 over 2, and that's what we substitute in. And this is where we eliminated the parameter, right? This is hence the name, eliminate the parameter. When we solve for it and plug it in, it eliminates it from the resulting equation. So we have 2 times y minus 1 over 2 plus 4. Here we can simplify this a little bit, right? The 2's cancel in that fraction, and so we get square root of y minus 3, right? Because it's -1 plus 4. And so that was our second step. Now we have, we plug t into the other equation, which is what eliminates the parameter. And now we solve for y in terms of x. And you can see we can square both sides here, add the 3 over, and what we'll get is y equals x squared plus 3. So this was our function. These parametric equations up here was describing just the parabola y equals x squared plus 3. So that's there's a pretty standard example of how you can eliminate the parameter to go from parametric equations to your just standard continuous function in x and y coordinates. And this, I say general here because this is the step, or these are the steps you'll want to do most of the time. Of course, with almost anything, there's exceptions. And here I want to make a notable exception for certain types of parametric functions or parametric equations. Here's a notable exception to the previous steps. A notable exception here is when you have something like, say, let's say x equals a times cosine of nt, where a and n are just real numbers, right? And y equals, say, b sine nt. For again, some time interval. I'm not going to write it down. Usually when it's sine and cosine, it's something periodic, like from 0 to 2 pi, or from -pi to pi, or something like this. But in any case, if you were to try, I mean, you could try the elimination method, you could try eliminating. So what would that look like? Well, let's just pick the x one here. Then we'd have cosine of nt equals x over a. So that would then give us t, solving for t explicitly, right? You have to undo the cosine and then divide by n. So when you undo cosine, you have to take arc cosine to both sides, right? So we get arc cosine of x over a, but then we divided by n to get t by itself. So that's all over n. And then we would have to plug this into y, right? So then we would get y equals b times sine of n. So we would have n times all this, which is over n. So the n would cancel. Okay, and then so we'll get, this is sine of arc cosine, which already is technically correct, but I have no idea. Like intuitively, this doesn't tell me much about the function. Like, you know, the whole point of this is to make your life easier or take something you don't understand in parametric equations, and it's something you do understand in rectangular coordinates. But here, this is worse to me, right? When I look at this, I'm more confused than I was up here. And so this is why we don't try elimination, or we can try it. It's why we don't really use it for this particular case. So here's what we can do. So we can be a little clever in this case. Okay, so I notice here that cosine and sine have the same function inside of, or we have the same entry inside the trig functions here. So we can say, we can do a little bit of solving here. We can say that cosine of nt is indeed x over a, and we can also say that y over b is sine of nt. And we can be clever with an old trig identity that we always use quite a bit. Remember, if these entries are the same for sine and cosine, we have the relation that sine squared of x, and for us, x is like nt, right? Plus cosine squared of x is 1. And we can use this trig identity in a clever way along with our parametric equations. So if we do that here, if we say, okay, well, sine squared plus cosine squared is 1. That means if I take cosine nt squared plus sine nt squared, so cosine squared of nt plus sine squared, this should be 1, and it is 1. However, we have relations that can eliminate this parameter t. We can say that cosine squared is x over a squared, and sine of nt is y over b squared, and this equals 1. And this is something I can work with. This is an ellipse. Where the horizontal radius of our ellipse, so it gives us, say, an ellipse, where the horizontal radius is A, and the vertical radius is B. And this is a lot better. This tells me so much more, and it's a lot more clean of an expression than what this was over here. And so that's why when there is an exception to the rules or to the steps I gave on the previous page, and it's when you see something of this form, you want to think trig identity to get to your function in rectangular coordinates. And here's a little remark down at the bottom that I can make. So I'm going to say when A and B are the same, and there's some number R squared, then the result, then you have x squared plus y squared equals r squared. The result is a circle of radius r. So these are a special type of parametric equations that we'll pretty constantly be interested in, and it's parametric equations for a circle. So this is a circle of radius r. So for example, if A was equal to B was equal to 1, then we'd have x squared plus y squared equals 1. And in rectangular coordinates, that is the equation for a circle of radius 1. So for the unit circle. And the parametric equations that would go along with this are, I'll write them up here, right? It would be, so we're looking at this. I guess I should say also, let's just look at when n equals 1, because if that number's higher, then it like maybe it wraps around twice or something, or half is slow or something. But let's just look at n equals 1 here. So then we would have x equals cosine t, y equals sine t, and this is from 0 to 2 pi. Standard convention is 0 to 2 pi. So you can think about our parameter t as being radians, right? So maybe you would like theta now instead of t or something. So this is a pretty prime example and one that's of interest to us. Okay, so I think I would like to break here for the first part of parametric equations. And in the next video, we'll pick up with going the other way, right? We went from parametric to rectangular. We'll see how to go from rectangular to parametric, and then a handful of examples, and then that'll wrap it up for parametric equations. And then in the second lecture, in the videos in the second lecture, we'll start to look at calculus with parametric equations. So I'll see you guys then.